Welcome everybody again to another session of our diffusion seminar series. We have two speakers here from two different parts of the world today. Jamshid Moshrefzadeh is joining us from Alaska, so I suppose it's very early for him. And Emma Burkett is from University of New Hampshire, so on the East Coast, maybe in the early morning. So both of them are really early career scientists because they are working on their PhD. So it'll be very good to hear some really exciting work in progress. So just for those of you who have not been in this seminar series before, the plan here is we have the first talk, then we take a few questions, then we move on to the second talk, and then we take questions on to the second talk, the first talk as well, and whatever discussion emerges out of it. So with that, I think I'll just go straight to introducing our first speaker. So Jamshid Moshrefzadeh did his BS at University of Wisconsin, and then he moved to Alaska in 2018, where he did a master's with Pavel Ispekov in 2020, I believe, and he's been working on his PhD, and he's a PhD candidate right now. And he'll be talking today about diffusion and growth rate chronometry provide constraints on timescales of magmatic processes at Bogoslof Volcano, Alaska. Jamshid, all yours.
Great. Thank you very much, Shumit. I'll share screen. Ooh, let's see. Yep. Okay, and then I'll go presentation. Can you see that okay?
Yeah.
Great. Okay, so thanks for having me. It's a big honor. I love the diffusion community, so I'm really glad that you host this seminar, and it's an honor to be a part of it. So I'll be talking today about diffusion chronometry at Bogoslof Volcano, which is in Alaska. But before I dive right in, I'll be giving a brief overview of the project that I'm working on for my PhD. It's a multidisciplinary project called the NSF Pre-Events Project, which stands for the Prediction of and Resilience Against Extreme Events, which is an eruption forecasting project that aims to develop volcanic eruption models and forecasts through this interdisciplinary synthesis. And it's a combination of 4 disciplinary groups, which are geodesy, seismology, gas, and geology broadly. So at the beginning of this project in 2020, they brought on 4 new PhD students, 1 for each discipline. So I'm representing the geology group or the petrology group. And the models that we create across these 8 volcanoes will ultimately be provided to the Alaska Volcano Observatory for operational use to aid in forecasting abilities and mitigate eruption hazards. So we're doing this by reanalyzing and combining the interdisciplinary data of previous eruptions across these 8 volcanoes. So all of the volcanoes will be in the Aleutian Arc or in Alaska. So this is the kind of geographic and geologic setting that we're looking at. So kind of the top part of the Ring of Fire, and subduction and magmatism here began around 46 million years ago. And it's important that we're studying volcanology here because we have over 130 volcanoes that have been active in the last 2 million years, and over 50 of them are historically active within the last few hundred years. So the volcano that we're going to be talking about today is Bogoslof, which is circled here in yellow. So we can kind of zoom in here and see that Bogoslof volcano is quite small. It's a back arc, predominantly submarine volcano, and it's about half a mile by a mile across. And its most recent eruption was in December 2016 until August of 2017. It was a 9-month-long eruption. And you can see from this side profile taken from a boat in the Bering Sea that there's multiple different like lava domes and features on the surface, but the summit of it is just about 100 meters above sea level. So it's actually quite a large volcano. It's just mostly underwater. And before I move on, I wanted to mention that Bogoslof has multiple indigenous names, including Agashagok, Agasagux, and Tanaxadagax. So as I mentioned, the most recent eruption in 2016 and 2017 occurred and produced three distinct lithologies, including basalt, trachyandesite, and trachyte. So these are all quite different. And on the total alkali silica diagram on the right-hand side, I've put these red ovals kind of grouping these three distinct lithologies. And the red dots are representing the most recent products, and then the other shapes and colors are representing historical eruptions or the dome material. So the basalt is primarily a scoria, the trachyandesite is a dome lava, and the trachyte is actually a pumice. So if you're like me and you like petrography, you can take a look at these high-resolution Nikon Coolpix scanner versions of the representative thin sections from each lithology, and see that the mineralogy of the basalt and the trachyandesite are primarily plagioclase, clinopyroxene, and amphibole, whereas the trachyte pumice contains plage and clinopyroxene, but then relic amphibole, so basically amphibole pseudomorphs, indicating that amphibole is no longer happy, and then also biotite, potassium feldspar, quartz, and titanite. Now, we published kind of a background petrology of this eruption in the Lowen et al. 2019 paper that I'm co-author on in Bulletin of Volcanology. But then what we wanted to do is build off of that because of the interesting presence of these distinct zonation in the crystals. And I know diffusion people were waiting to see this type of zonation in the crystals. So we have these in different lithologies. In the top row in the basalt, we have both normally and reversely zoned clinopyroxene in addition to the trachyandesite, and then distinctly zoned plagioclase crystals as well. So if you're not familiar with the diffusion chronometry and the general background of this methodology, the reason why this is interesting to us is because minerals in the magma system are acting as record keepers for the conditions. So if there are any perturbation in those conditions, such as changes in temperature, pressure, or oxygen fugacity, magma composition, etc., those can be made evident by sudden compositional and or textural changes in those resonant crystals. And I kind of like to think of this as a tree rings where the crystals are growing from the inside out. And then if you look at a cross section of a tree, you can maybe tell when there was a forest fire or events such as that. So that's the kind of detective work that petrologists are trying to do by looking at the chemical and textural composition of crystals. So a kind of classic example of such perturbation is magma recharge. So if you bear with me as I show this elementary cartoon, you can envision that there's some sort of magma reservoir floating somewhere in the crust, and there's a bunch of crystals that are growing at one nice homogeneous and euhedral composition because they're happy at this temperature pressure condition. And then suddenly you will have the intrusion of new magma coming from depth, and this magma may be a different temperature, a different composition, and it pressurizes the system. So there's a series of different events that may occur as this magma is intruding into the shallow reservoir. And keep in mind that this intruding magma may have crystals of its own in its cargo, and they may be the same type of crystal, but growing at a different composition. So in this cartoon, we have the resonant crystals growing at a light blue, and the intruding magma with crystals that are a sort of dark blue. So then the idea is that as these two magmas mingle or possibly mix, you have the crystals start to grow new rims that then the light crystals of the resident magma may begin to grow rims that are similar in composition to the intruding crystals, and the opposite is true for crystals hosted in the intruding magma. And this is a very simple idea of how you may be able to get both normally and reversely zoned crystals that are recording timescales of the same magmatic process. So the reason why this interests us for diffusion purposes is because over time, this is what that crystal would look like. That before the conditional change, it's just one composition. Then right when that perturbation occurs, the crystal forms a rim that is distinct in composition relative to the core. Then over time, these two zones will diffuse into one another due to diffusional relaxation. So the idea is that the profile smoothens over time because these two zones are driven into one another due to the presence of a chemical potential gradient. So over time, the stepwise boundary will relax as it attempts to reach some sort of a homogeneity. So then as a diffusion chronometry people, we can take transects across these crystals and then allow us to model the diffusion timescales. So if we take a transect and we see this sort of a dashed line, we can then model how long ago that profile was stepwise to determine how long ago that boundary formed. So the reason why we wanted to apply this at Bogoslof for the most recent eruption is because these products provide this very awesome opportunity to apply diffusion chronometry because of the abundance of these formerly stepwise boundaries within the mineral phases. So this is exactly what we did, and we primarily are targeting clinopyroxene because the diffusion parameters are most well constrained. Of course, olivine is the king of igneous diffusion, but there's no olivine in the samples. And we're also focusing on the basalt because that's the abundant lithology that erupted in 2016 and 2017, and is also the driving force of the eruption. So we're going to be using the diffusion in clinopyroxenes from the basalt. So in order to analyze our samples, we took all of our carbon-coated thin sections and went to the electron probe microanalyzer, or just the microprobe, at the University of Alaska Fairbanks Advanced Instrumentation Laboratory. And the microprobe bombards samples with an electron beam and measures the resulting X-rays with its 5 spectrometers. And simply, it's the reason why we prefer the microprobe is because it has superb spatial resolution and it is non-destructive, unlike laser ablation. And since we're looking at magnesium and iron interdiffusion, we don't need to worry about trace element diffusion. So the microprobe works excellently for our purposes. So that's the reasoning why we're using that. And of course, we need to worry about the different diffusion modeling parameters for looking at these clinopyroxenes in the Bogoslof basalt. So as we know, diffusion in solids is predominantly controlled by temperature. So that's the main thing that we'll have to constrain. It also varies depending on the crystallographic axes of the target crystal that you're looking at, but we can determine a relevant diffusion coefficient by accounting for these variables and including the experimentally derived values and getting the temperature from various geothermometers. So for our purposes, we obtained the pre-eruptive temperature and oxygen fugacity from iron titanium oxide pairs from the Gearso and Evans geothermometer, and we got those from magnetite ilmenite pairs in the trachyte pumice. Now, you may say, I thought you said that you're modeling diffusion in the basalt. Why are you using temperature from the trachyte pumice? These are very distinct lavas, so why would I be able to use the temperature from this on this? Well, you don't just have to take my word for it, because now as we move into the results, I will try to convince you that that is the correct temperature to use in this case. So if we take a look back at this total alkali silica diagram, you can see that the trachyte composition has not been erupted at Bogoslof since 1796 Castle Rock, as shown by these yellow dots here. Now, I know that on the total alkali silica diagram, these plot in what you would call a trachyandesite, but in our previous paper, we showed that major and trace element compositions between the trachyte erupted in 2016, 2017 overlap with this Castle Rock dome that erupted hundreds of years ago. So as we take a look at this trachyte pumice, we did modal analyses that reveals that it is 90% crystalline. Now, I am no expert on volcanoes such as Yellowstone that are highly crystalline, but one thing I do know is that something that's 90% crystalline is assumed to be uneruptible. So it is interesting then that this pumice was 90% crystalline, but the ground mass is microlite-free glass. And so it's quite an interesting rock, actually. And the presence of potassium feldspar and quartz and titanite are suggesting a low temperature eutectic crystallization. So why then are results from iron and titanium oxides overlapping with temperatures that you would expect from an amphibole plagioclase-bearing basalt? The temperatures from the trachyte that are ranging from 977 to 1056 degrees centigrade. So this was alarming and interesting to us. So now I will try to indicate that there was a basalt rejuvenation that re-equilibrated the trachyte to basaltic temperatures. And you can see this in hand sample here, where you have the basalt scoria and the trachyte is actually mingled with it. So this is macroscopic evidence in hand sample. And then on the surface of the volcano itself, you can see much larger bombs that are showing this phenomenon as well. In addition, you have these small pummices with these little inclusions here, which is about 2 to 8 millimeters, and they're mafic inclusions that are suspended in a glassy strands of trachyte that are in the center of distinctly large vesicles. You can see the normal vesicle sizes in the pumice, and then these are abnormally large. So we assume and we infer actually that this is due to heterogeneous bubble nucleation at the surface of a hot lithic fragment based off of the work of Gardner and Dennis in 2004. So all of these are indicating, are supporting our hypothesis. And then if, like me, you prefer microscopic evidence, you can take a look at these backscatter electron images, where on the left-hand side, we have a quartz crystal that's hosted in a trachyte pumice with a very clear dissolution rim, which is probably a result of heating. And my personal favorite here in the middle is a quartz xenocrystal. So this is actually a quartz in basalt. So my training from geology 101 and mineralogy back in the day was cringing when I saw a quartz inside of a basalt, but you can see that this quartz actually has a reaction rim. So this is indicative of quartz coming from somewhere else and not belonging there. And then finally, here's just a zoomed up picture of one of these amphibole pseudomorphs in the trachyte pumice that I mentioned towards the beginning, showing that this amphibole may have been happy in the trachyte, but then triggered but then when it was triggered by the mafic recharge, it dissolved into these observed pseudomorphs. So one other way that we may be able to see any temperature relation of the trachyte and the basalt is by doing two feldspar thermometry of the feldspars that are in the trachyte. So we used sanidine and plagioclase microlite compositions to calculate a temperature of approximately 870 degrees centigrade. Now this is much colder. And this is probably closer to what you might expect for a trachyte pumice. So the explanation for this is that the two feldspar thermometry re-equilibrates much slower than iron titanium oxides. Studies have shown that iron titanium oxides can fully thermally re-equilibrate in the timescale of weeks, which is more than enough time for the oxides in the observed trachyte to re-equilibrate to the basaltic temperatures, because this eruption occurred over the course of 9 months. Now, since the feldspars equilibrate much more slowly, we interpret that these results are capturing a range of temperatures between the original cold trachyte and the contrastingly hot temperature of the juvenile basalt. So ultimately, all of this evidence is suggesting that the trachyte was re-equilibrated to the temperature of the host basaltic magma, which rapidly heated the trachyte and created a limited amount of melt, which caused inflation of residual volatiles. And thus, we use the 1056 degrees Celsius from the iron titanium thermometry in the trachyte to describe the pre-eruptive temperature of the basalt, because this would serve, the maximum temperature from trachyte would serve as the minimum temperature of the basalt. So if you believe me there, we can go ahead and say that that's the temperature that we should use for diffusion modeling in the basalt, and we applied it. So here's the crystals, and so I'm modeling this profile from core to rim, from left to right. So the yellow dots are representing the natural composition from the electron microprobe, and the orange line is representing the best fit from our models, and the resulting time scale for this crystal in particular is about 112 days. So we analyzed all of the different clinopyroxene crystals that we had targeted, but as we were analyzing them and studying the samples, we also noticed the presence of these multi-phase crystal clusters. So these, there's multiple different ways that crystal clusters can form, but I won't dive into them. I suggest either looking at the old Vance papers from maybe 1969, or looking at Tom Shea's presentations in the past. So this diagram on the right-hand side is based off of one of Tom Shea's AGU presentations describing the three main ways that crystal clusters form, but we're going to be focusing just on growth, where the cores are fixed to one another and the rims are growing simultaneously. So within these crystal clusters, we have these distinct boundaries that are traceable between cores and rims across different phases. And the interpretation is that the cores were affixed to one another and then contemporaneously formed their contrasting rims once they underwent the same changes in the magmatic system. So an example of this can be shown in this crystal cluster here. And the scale bar isn't showing up, but this is about 100 microns, this distance here. But you can see that there's a clinopyroxene, a plagioclase, and an amphibole all affixed to one another. And what I'm trying to draw your attention to is that the distinct rim of the clinopyroxene lines up with the rim of the plagioclase, and then that sodic rim of the plagioclase aligns with the reaction rim of the amphibole. In a more simplified cartoon, you can see on this figure that as plagioclase and clinopyroxene become less mafic, the amphibole begins to break down. And then you can use diffusion chronometry on the affixed clinopyroxenes in these multi-phase crystal cloths to determine the growth rates for plagioclase rims and the amphibole reaction rims, assuming that these rims have formed contemporaneously. So you have a precise timescale of that core rim boundary from the established clinopyroxene diffusion chronometry. And then just by measuring the width of the affixed crystals, you can determine the natural apparent growth rate of the affixed crystals. So the amphibole reaction rims are a little bit more complicated because it's a breakdown process rather than a growth process. So we use then a technique that we call growth rate chronometry. By measuring the width of the affixed plagioclases, you can determine the timescales of magmatic processes that formed the boundary between the core and the rim, assuming a constant growth rate. And I will say that our growth rate of plagioclase that we calculated here is similar to experimental results of plagioclase growth. So we use these two petrochronometers, the diffusion chronometry and our so-called growth rate chronometry, to then determine timescales of magmatic processes. And you can see from the histograms on the right that our timescales overall are overlapping with one another, showing that these zones and minerals are forming during the course of the most recent eruption, because again, it's a 9-month-long eruption and our oldest timescale is less than 180 days old. So then if we take these timescales and subtract them from the day that the samples erupted, which is the end of August of 2017, you can go back in time with the blue dots representing plagioclase timescales and the orange diamonds representing clinopyroxene, and you can see that our oldest timescales correlate to around March of 2017. The error bars on this are quite large, as is kind of common in diffusion, but the clinopyroxene error bars are based on the uncertainty in the modeling temperature, and the error bars on plagioclase are based off of the standard deviation of the measured rim widths. So now we can compare this with date on the x-axis to other interdisciplinary monitoring data to perform petrologic monitoring. And we can see on this next figure, oh, it went too hard. There we go. We can see on this figure here that these results of ours seemingly correlate with increases in both seismic activity and SO2 emissions. So if you look at our oldest timescales, which correlate with March of 2017, if you go up into earthquakes per day, you can see a spike in the seismic activity, as well as the largest SO2 mass flux event that occurred contemporaneously with our oldest diffusion timescales events. So this means that some sort of change in the eruption style began around March of 2017, and we interpret the chemistry of these crystals as well as the timescales to indicate that these distinct rims in all the crystal phases formed due to ascent-driven magma decompression, which was followed by shallow emplacement of the mafic magma, which occurred continually throughout the course of the eruption. And all of these are ending up in the shallow cryptodome, which is why you get a range of 200 or less days as the timescale, even though they're all erupting at the same time. And ultimately, this led to us forming this very simple cartoon model where you have a Bogoslof at the surface, and you can actually see the cryptodome on the surface here. And then the updated model from our Lowen et al. 2019 paper for this is shown zoomed in on the right-hand side, where you have this basalt pre-eruptive storage area where plage, clinopyroxene, and amphibole are crystallizing, and then they suddenly ascend and experience ascent-tripping decompression and begin to form their distinct rims. And somewhere throughout their ascent, they rejuvenate and recycle this partially rejuvenated trachyte reservoir, which fed the Castle Rock eruption hundreds of years ago. And then ultimately, they are intruded into this shallow cryptodome where diffusion records residence times of the crystals of the stepwise boundaries, and the amphibole is breaking down at this low pressure environment due to the ascent. So as to conclude, we have the products of this eruption, which provided us with this awesome opportunity to identify the processes for the formation of the chemical boundaries across the multiple different mineral phases. And we were able to use the established pyroxene diffusion chronometry technique to calculate a growth rate of plagioclase and amphibole and develop a new tool called growth rate chronometry, which allows us to analyze many crystals much more rapidly, because instead of taking a lot of analytical time and cost by doing core rim transects on pyroxenes, for example, you can simply take BSE images of countless plagioclase crystals and then measure their rims to get timescales of magmatic processes. So this paper is kind of a proof of concept of the theory. And then both of our petrochronometers are powerful tools to analyze the phenocrysts and to constrain timescales of magmatic processes. And ultimately, the goal of the pre-events project is to do interdisciplinary synthesis, and our results indicate that changes in the traditional monitoring data may be directly related to perturbations in the conditions of the magmatic system as recorded by diffusion chronometry. So this paper was recently published as my first author paper in JVGR. So please go ahead and scan the QR code if you would like to take a look at it. And with the diffusion pun in mind, I'll say thank you for your time.
Thank you so much, Jamshid. That was a very nice and clear summary of a volcano and a set of different methods, and then tying it into monitoring data. So a lot of good stuff packed into short timescales. So a few quick questions maybe for Jamshid before we move on. Yeah, Lidrik, go ahead.
Hi, thank you very much for your presentation. Do you hear me?
Yeah, I do. Yes, thank you.
It was nice. I'm wondering, I have one question related to the textures or to the chemical variations in your clinopyroxenes, because you are modeling a nice profile, but according to the BSE images, we can see that in the outer part of the clinopyroxenes, there's several tiny zonations. So I'm wondering what we could do with that, if we could play with it. And I expect that those may document similar timescales. It's likely documenting other processes, but which should record the same timescales. Have you tried something related to that?
Yep, this is a great question. So the clinopyroxene crystals that I show, I'm modeling the most distinct boundary, which is it leaves quite a thick rim. But when you look at them, you can see that. I wonder if I can pull up the image that I was referring to here. Yeah, so this is the boundary that I'm looking at, because you can see a nice, beautiful homogeneous core if you ignore the sector zoning here. But I totally see your point that there's many different processes that are occurring to form the different subtle zoning in the rim. But what our argument is for that is that the change in magnesium number across this rather thick rim is so subtle that it's not statistically significant, at least for our purposes, to model diffusion between them compared to the change in magnesium number between the core and this wide rim. So our argument is that these are just subtle variations that are occurring during this time scale of it sitting in the shallow cryptodome area. And you would need, you can only get like maybe 1 point from the electron microprobe in each of these rims, if that. So it's a lot easier to say that this is homogeneous and this is homogeneous, and just kind of take the average, because even in these few microns here, you can see that there's some variation, but it could be just due to growth. And ultimately, the diffusion that we're looking at is only occurring within like the few microns on either side of that boundary. So that's the main targeted boundary for our purposes. But I agree with you that this is, of course, any scientific endeavor has many assumptions, and this is just one of our weaknesses, is that we have to assume that that thick rim grew quickly, and that it's homogeneous for our purposes. But it is worth noting, definitely. I hope that answers your question.
Yeah, perfectly. Thanks. And maybe I have a short, quick question related to this slide. Maybe you told that and I missed it, sorry. But have you tried to use the grayscale to modelize this profile? Because when we see the best fit you have, finally, we may wonder what would be the profile if you would have a better resolution in terms of point measurements, and image analysis could help. And maybe you spoke about that. Sorry if I missed it.
Definitely. No, I didn't mention that, but thank you for bringing it up, because I failed to mention it, that we actually do use calibrated grayscale values. I just don't plot them here. So we've plotted the yellow dots because I like to show the resolution of the electron microprobe. So we take points every 2 microns, which is a pretty good resolution. So that takes a lot of analytical time. So you can see these red lines are where our transects are taken, and the circles are actually every point. So we do a calibrated grayscale to fill in the gaps, and so that's we use the calibrated backscatter electron transects to do the diffusion modeling. I just remove them afterwards so that you can see the natural points better. So it's just an aesthetic choice of mine, but forgive me for not mentioning that for the diffusion modeling parameters. We do use that because that is crucial. You're totally right about getting better spatial resolution.
No problem. Thank you very much.
Thank you. That's good clarification, actually. One more quick thing, if somebody has something burning for Jamshid before we move on. Ralph, yes.
Yeah, hello, Jamshid.
Hi, Ralph.
Again. Yeah, very clear talk, as Schumann already mentioned. I was wondering if here in this case you could also use the magnesium in plagioclase thermometer to get information of the temperature. So the magnesium exchange between CPX and plagioclase, and also maybe even if there's some zoning of magnesium plagioclase, that would be another option.
That would be great. I haven't looked into it yet, but my final PhD project is again on Bogoslof, so I'll take a look at that. Thank you for I'm making a note. Great.
And while you're at it, you could also try modeling magnesium in plagioclase for diffusion.
Of course. Yeah, that I think would be a great thing to do, is to compare the time scale of magnesium diffusion in plagioclase compared to our growth rate, to see if that is kind of supports.
Okay, so I'll let people think about more questions and things, but we can slowly move on to the next talk. So let me try to stop you sharing.
I think I did. There we go.
Yeah, no, you are okay. I just have to get my screens in order here now. So let me just go to, I just shared the whole thing here. So yeah, so move on to the second talk today. That's Emma Burkett at the University of New Hampshire. And she's also working on her PhD with Julie Price. And Emma did her BS at Western Washington University and moved across the country, I guess, also in 2020 to No, so she moved across the country and did her master's also in 2020 at University of New Hampshire, and is a PhD student currently there working on the topic that she'll be talking about. So her talk is on MSURFED magmatic speedometry using R-coded fitted elemental diffusion modeling, insights into the dynamics of transcrustal magma systems. So Emma, I'll stop sharing and you can start sharing your screen.
All righty.
Yeah, looks good.
All right, how's that look?
That looks very good.
Perfect. All right, thank you so much for that introduction. And I'm really excited to share what I've been working on for the past couple of years with the diffusion community, who it's really applicable to. It's fun to be around other people who do the same thing. Before I get started, I just want to mention that this model was co-developed between myself and my advisor, Julie Bryce, and then also a UNH data science faculty member named Fani Kandami. So he's done a whole lot with me and does not take as much credit as he should. This talk is pretty code heavy, so I'll try not to get into the nitty gritty and try to keep it a little bit on the short side. All right, so MSURFED is just another model, another tool to process large amounts of collected data to study how magma is stored and moves the crust before eruption. And to explain MSURFED, I want to make sure we're all on the same page with what diffusion chronometry is, which I'm pretty sure we are, but we'll just do it for the sake of doing it. And then I'm going to lay out how MSURFED is different, what it's good at, what it's not so good at, and then see MSURFED in action for processing some pilot data sets from Augustine Volcano and some pre-climatic eruptions from Mount Mazama. So again, I know we're all kind of familiar with this, and Jamshid did a great job as well, so I'm just going to pretty much repeat everything he just said. But crystals are mini diaries recording changes in the magma chamber line by line until that crystal is removed through the system through an eruption. And then diffusion chronometry is the method of reading those diary entries and putting timescales on them, and then we can get fine temporal resolution to link those crystal records to superficial expressions of volcanic activity, such as seismic and gas emissions, which this little animation is showing. So when those changes in the magma chamber occur, we can measure the concentration of different elements across the transect of a crystal, which will initially look like hard steps. And as that crystal sits in the magma chamber, that clock starts ticking by that sharp step function, starting to relax as those elements reach equilibrium through diffusion. And then we can plot our collected data, whichever method you're using, onto these profiles to find which slope it matches best to, find that best fit, and then correlate that slope to a specific time interval in which that crystal was hanging out in the magma chamber. So when I started my master's, this is what my diffusion modeling journey looked like in 2018. And at that time, the only options I could really find of how to process diffusion data was through Costa's Excel sheets, which was a super great service for providing these sheets and these tools. I wasn't using Alvine, so I learned all the ins and outs of these Excel sheets, of changing those equations, making them applicable to the things I was using. And then I would drag the cells out as far as I could because I was not a coder at this point in my life. And then I would wiggle match by eye my collected data with the little plot there of the predicted concentrations. And one profile would take me quite a while, especially because I would get the spinning wheel of death a lot, which meant my computer crashed a lot of times, which led to me buying a new computer as well, but it was quite frustrating. And after too many times, I thought to myself, there's got to be a way to do this. And that's when I reached out to Fani. And this was about the same time when the COVID pandemic was really starting to kick up. So this is a perfect time to spend my working hours coding instead of doing lab analyses. Kind of not by choice, but this is where we went. And this led me to our programming language. And after months of tweaking and adjusting and rerunning the code, this is where MSURFED kind of came to be. So again, MSURFED stands for Magmatic Speedometry using R-coded fitted elemental diffusion. And so MSURFED is really designed for non-coders in mind. The way the code is written is into little chunks that's broken down step by step with detailed descriptions of what each chunk is doing. And the code is also adjustable for whatever application you're doing. So whether it's magnesium and pledge or iron, magnesium, and olivine, or you're doing melt embayments, whatever it is, it can be tweaked for whatever you want to do. So this is the logic model behind MSURFED, and I know this is a lot to process in one slide, so forgive me for that. And I can share this with people later if you want to peer over it then. But what I really want to focus on and emphasize is that MSURFED isn't totally automatic. There is manual calculation of diffusivity inputs, like the assumed initial concentration. It doesn't solve that for you. You have to do that on your own. And you also have to choose the diffusivity equations that you want to use, and then how many time steps you want that model to run. And I hope that these manual inputs will act as a check for misinterpretations of the model. So it can't just be used as a hammer on any kind of, whether it's a screw or a nail or staple, whatever it is, that it's being used properly. And the cookbook recipe style of this code also encourages familiarity with coding, especially for early career researchers or anyone who's not super familiar with coding. All right, so the R in MSURFED does stand for R, programming. And I know that most of the people in our community use Python, but with the advice of my data science collaborator, Fani, he suggested writing this in R because it's better for processing large amounts of data quickly. And since he runs a lot of big data a lot of the time, I took his word for it, and turns out he was right. So another benefit with R is that it is free. And the way this code is written is in an R markdown file, which basically means, if you're not familiar with R, that it breaks it up into separate little chunks of code. And I hope that will prevent large freeze ups. Because one of my most frustrating things with writing code is if you just misplace one little like comma or something, the whole thing doesn't work and you don't know where that error is. But having it in small little chunks can be easier to find those errors as you're working through it. So R can also be used across Windows and Mac operating systems. And then R is also faster at processing large data sets compared to Python. So this is looking at, this chart right here is looking at an input table at the vertical axis here, and then how long that function takes. And in seconds on the horizontal. So this is comparing two different things in R, which is the data table and Dippler, and then Pandas is with Python. And here, especially at the top, this is the largest data set. R is much faster than Python. So smaller data sets, they're a little bit more similar, but when we start dealing with those huge data sets, R is quite a bit faster. So MSURFED is not existing in a vacuum. It's not the only diffusion model out there. And it's also not the best. So here's kind of the trade-offs between the model choices and the different programming languages as well. So like I said, MSURFED is in R. R is not as popular. Like I said, most people use Python. So it's not as intuitive, and it is slower than MATLAB. But it is faster than Python, like I just showed you, running those huge data sets. The Defense is another model, and it's in Python language. One caveat with Python is sometimes there can be memory timeouts when running too large of data sets. But like I said, this is the most frequently used coding language. And then NIDIS is in MATLAB language, which requires a license, so it's not free or open sourced. But MATLAB is the fastest at processing data sets across the board. And then Dippler is another model that's really great. It's a software interface, but it only runs on Windows, and I'm a Mac gal, so I couldn't use it, which I was really excited to, but I wasn't able to when I started my diffusion path. And what's great about it is it doesn't require coding skills. So each model really runs best when you have a specific goal in mind, in my opinion. So MSURFED is really designed to use multiple temperatures to avoid overprescribing storage conditions. Defense is great for removing propagated error, really narrowing down on what those possible residence times are for the crystals. NIDAS is a non-isothermal model, so this is perfect for multi-stage zone crystals. In DIPRA, because it's a user interface, it really builds that familiarity with numerical models, especially as someone who is just starting their diffusion journey. So before deciding which model to use, a user should choose based on the magmatic system that they're working in and which model would be a best applicable or the best tool. So MSURFED is really optimal for vertically extensive systems or ones that have geochemically separated magma pods. So we could have a huge range of possible storage temperatures. But other models are maybe more suited for more defined magmatic systems where temperature is well defined, and we know how or where those crystals might be stored. All right, so that's enough about the coding kind of thing. So now we're going to see more of the code in action in some pilot data sets. So the first data set is with Augustine Volcano. So it's a little bit smaller, but it's one of the most active Aleutian volcanoes. And this is where I did most of my master's work, started here in Augustine. It's very crystal rich and has heterogeneous products, which is a high silica and a low silica rich andesite. And instead of a central magma chamber, it has a really complex plexus of dikes that kind of stalls little slugs of magma within this complex system, which are then remobilized in the next eruption. And it has quite a large range of storage temperatures from 670 to 800 degrees C, and that's from Coombs and Vasquez. So where is Augustine? It's in Alaska, and it's near the mouth of Cook Inlet, just west of Homer. And this volcanism here is sourced from the Aleutian volcanic arc, which I won't go into much detail because Jamshid did a great job on that one. But this study specifically, we're going to look at the two end member compositions of a high silica andesite and a low silica andesite. So the high silica is more on the north side of the island, and the low silica andesite is more towards the southwest. All right, so here are some results. So where Augustine, or where MSURFED really came from, was when I was trying to process all this data for the Augustine 2006 eruption. And like I said, there's a large range of possible storage temperatures. So it was really hard for me to figure out which one to choose when I was doing my diffusion models. So I kind of just decided, let's do them all. And that's where MSURFED really came out of this. And these results are from laser ablation methods in our lab. So you can see those pits in the crystals here. And this is a orthopyroxene and then a plage here on the bottom. So after finding all of the best fits through the MSURFED code, and this is from the collected concentrations of chromium in OPX on the vertical with distance from the core on the horizontal axis, and then magnesium concentrations in plage with, again, the distance from the core on the horizontal. And then we get this huge hex plot at the end. Again, this is all the slew of temperatures that you could possibly be with the Augustine system on the horizontal axis, and the magmatic pacing time on the vertical. And what I really want to zero in is how these two different mineral phases compare. And to try to have some kind of control to compare these times with, I used the uranium, thorium, zircon ages from Coombs and Vasquez as well. And so here, there's these histogram plots on the side. So this is showing the range in temperature and the density of where those temperatures are. And then on the vertical is the range of the different pacing times. So here, what I want you to focus on is the overlap with the pyroxenes at these really high temperatures. There's more dense, darker colors overlapping here with the zircon age, more on this top right corner. So we see these high temperatures where plagioclase is kind of overlapping with those zircon ages at much lower temperatures. And then if we're just looking at the vertical axis, the pyroxenes have much longer residence times, but the plage has much shorter magmatic pacing events. So we kind of have two different magmatic storage conditions. And I have a cold system with short short ages but cold temperatures and warm storage conditions with long ages and hot temperatures. So how do I reconcile these two conditions? And the way I do that for right now is with a vertically extensive system that would accommodate the varied storage conditions in that system. With the plage, which is a little less dense and more dominant in the upper crust, supporting a more cold storage system, and the pyroxene, which is relatively more dense, sinking more towards the lower regions, and crystals with higher temperatures, supporting that warm storage deeper within still the upper crust, because here we have the depth. The Augustine system is still pretty shallow, so we're not in the deep, deep crust, but just the deeper upper crust. So if we just zoom in to this cold storage zone, as I'm calling it, there's some frozen mini plutons that are then remobilized by basaltic recharge. And this is also supported by iron-rich rims and plage, with, again, the relatively lighter plage recording these cold storage conditions. And then zooming down to the warm storage zone, I'm thinking that the heavier zircons and the pyroxene are recording the much longer residence times with warmer temperatures. And there's also some plage hanging out down there with multiple recharge events that's recorded through oscillatory zoning. So that's the complicated story that is Augustine as of right now. So now we're going to switch to a different system of Mount Mazama or Crater Lake. So this is a much different volcanic system where it's a caldera forming event that happened 7.7 thousand years ago. It has a much longer eruptive history than Augustine. We're over 400,000 years. And instead of that complicated mess of dikes and sills, it has more of a central chamber with a thermal and a density gradient, and a little bit smaller temperature range of possible storage temperatures from 850 to 960. So Mount Mazama or Crater Lake is located in Oregon, just north of the border of California and Cascadia. So this volcanism is through the subduction of the Juan de Fuca and Gorda plate beneath the North American plate with the extensional forces on basin and range provinces. And all of those tectonic forces generate a volcanically active area that's 30 kilometers wide and 40 kilometers long. And this volcano has effusive and explosive eruptions with a slew of different compositions. But this study right here, this pilot data set, is just going to be focused on two mafic compositions that were erupted before the caldera forming event. And that is going to be the red cone here that's highlighted at the top, and then the Castle Point unit as well, more on the bottom of that little map. So Castle or Red Cone happened about 35,000 years ago, and Castle Point is relatively dated 14 to 16,000 years ago. And here's on this plot, here's the climactic Mount Mazama eruption forming Crater Lake, and here's Castle Point at that 14 to 16, and Red Cone that is slightly older. And why are we using these units? Because they're not the big eruption that everybody likes, but these units can give us insight into the pre-eruptive storage conditions during the magma assembly process prior to that caldera forming event 7,000 years ago. So like I said, this is a pilot data set, so give me a little bit of grace here, but this study just uses chromium concentrations in OPX. And from here, we see the best fit from both the Red Cone and Castle Point. So here is an example of one of those profiles in OPX, so again, with the concentration on the vertical and distance from the core on the horizontal. And since this is a little bit smaller population size, crystal-wise, and it has a little bit smaller temperature range than Augustine, I decided to use a cumulative frequency plot instead of a hexagon density to visualize these results. So that's why it looks a little bit different here. So looking here, we've got the frequency on the vertical and then those diffusion timescales on the horizontal, and then it's colored by each sample or each crystal transect. So we see really large residence times for the best fit from like order of 10,000 years to like 1,000,000 years. So really long diffusion timescales with these orthopyroxene crystals. So like I said, this is a small data set. So moving forward, this data set We're going to add more crystal phases to see how like olivine would compare, because there is olivine here. We just didn't do it with this pilot data set. And then adding or possibly looking at just one temperature or a couple temperatures and putting that through a different model to see how that error would be removed and then how it can compare to these pilot data set results. All right, so what's next for the MSURFED model? I'm still validating it with other results and comparing those results from other models in previously published studies, just to see how it compares, because it doesn't do the fancy statistics beforehand, but kind of looks at it afterwards. And then I also want to test MSURFED on different lab methods. So like I said, I use laser ablation, but how does it perform using closely spaced data like EPMA or BSE imagery, as Jamshid beautifully presented prior to this. So how does it look with those kind of data? And then once this work has been published, the code is going to be shared on GitHub, so it'll be accessible and open access. And then to increase that accessibility, I'm going to be sharing MSURFED with SC4Grabs webinar workshops. So if you haven't heard of SC4Grads, we're a subgroup of the research network SC4D, but we're focused on early career researchers, really trying to build community, mentorship, and sharing these skill sets. So if you want to learn more, shout out for SC4Grads. We're a great group of people. And if you want to learn more about us, you can scan that QR code, or if you have students who want to meet other students, you can send them our way, and we have all sorts of webinars and workshops working and in the works, trying to really build up that community. All right, so I'm kind of wrapping it up pretty short here, but in summary, MSURFED really optimizes diffusion chronometry across different crystal phases. Like I said, you can use whatever kind of crystal you want. You just got to tweak it a little bit, but it's pretty self-explanatory and kind of guides you through it with all of that to give you insight into the magma assembly process for different systems. But MSURFED is really ideal for complicated magmatic systems because it can handle a large set of geochemical data. So you can give it a huge range of temperatures, and it can process each of those temperatures for a crystal transect, ranging from 750 all the way to 900, and it can do it pretty quickly. So that way you can look at all the different possible temperature conditions and then see how those residence times compare at the different temperatures. So with that, I will leave the rest of the time for questions. And I also have a ton of stickers of this little MSURFED icon. So if you want one of them, let me know and we'll figure how to get them to you, because I have a whole bunch. But that's the end for me.
Thank you, Emma. That's a lot of very useful information, useful resources, and yeah, very generous of you to try to share the little MSURF logo. So I guess the easiest way would be to type it in or write a mail to Emma later, but questions now. I mean, I already see one thing that we would need to have you come back and do is to do a demo of MSURFED at some point, yeah. How you actually go about doing the thing. But that's, for another session. Now, questions for Emma on things to do. Well, if people are thinking about it, yeah, go ahead, Ralph. Yeah.
Yeah, so you mentioned there's some input, some input data required, some decisions that the applicant has to make. For example, initial conditions, you have to think about the initial conditions, but also what about the boundary conditions, how you deal with this, with the different type of boundary conditions possible?
Yeah, so that's a great question. So this code doesn't solve the boundary conditions for you. So I know there's a lot of assumptions that we make. So that has to be done kind of beforehand. So when you input your data into the code, It kind of explains what all you need before you input into it. But one of them is your boundary conditions, and how you set them up, and how that influences your initial concentration of profile that it's going to compare to. So that is still, this code doesn't solve that problem. I wish it did, but it doesn't.
No, it can't. I mean, this is, I completely agree. This is a decision that one has to make for a given system.
Yeah, and they're all
That's simply like fixed boundary condition, or is it a closed system or whatever? So these kind of things you have to think about yourself before you apply code like that, I think.
definitely.
I think it's good to leave petrology some work and not let the computer take over.
Exactly. Yeah, exactly. Still need the petrology context, and I use thick sections and crystal mounts, but you still got to have like some of those thin sections to do the context of, you can't just apply numbers and then have the computer spit it out in the end. You still got to read the chapter in the book that it's in to figure out what the story is.
Yeah, absolutely. Lidrik, you have a question?
Yes, thanks. Thank you very much for your presentation. Could you please come back to the slide where you have the time versus with all the small dots, you know, where you have the different minerals estimation?
Yes.
I'm wondering if you have in yes, this one. Thank you very much. I'm wondering if you have in your software the possibility to highlight the quality of the fits, because now we have, for example, in this figure, plenty of points, but likely some of them are very good fits, well-modeled profiles, and some are maybe of less quality. For example, to the left, if we look to the left, this chromium profile is not very nice, let's say, and the magnesium one is probably largely better. And if you have a way with the program to highlight the quality of those models.
Yeah, that's a great point. And we've been thinking about that. And I think that is what we're going to be working on after we tweak this and polish it up a little bit more, this version. We want to add that in. So right now, the range how it finds the best fit, it takes into account the range from the instrument, but it doesn't weight each point by the goodness of fit. So that's what we're working on next, is exactly that point of to weigh the points that are better fits heavier. So there'll be a darker color in this plot than the ones that don't have as great of a fit. But I think that also, at least in the current stage that it's in right now, that circles back to the petrology and you need to look at the data that you collected before you shove it through the coding, because the coding isn't going to fix the best fit problem for you. If it don't fit, it don't fit. But
for example, what does the program do, or what can we do with the orthopyroxene chromium profile here? Because for me, it's not fitting. Is it because of the initial profile or because of our parameters? Can we extract or remove the result of this one, for example, from easily with the program?
Yeah, it doesn't do that for you as of right now. But that is a really great point of kind of digesting and looking through the data before you plug it into the program and looking too, is it actually a diffusion profile, or is it, the growth of spinel instead of actually chromium diffusing through the pyroxene? But yeah, I think that goes back to, you need to look at the data that you've collected and think about it in the petrologic context before you just plot everything and call it a best fit. But that's a really good point of how it needs to weigh it quantitatively, the goodness of fit, and making the better fits like a stronger argument for a good magmatic pacing time.
And last quick question, sorry. The initial profile, you have to define it manually, or how does it work?
Nope, you had to do that manually. So how I did these ones for this data set, I did the max and the maximum and the minimum for the chromium. So I was making that assumption. I could have taken the average, That's like right here. I could have taken the average of those, but instead I chose the minimum. And I could have called this, you know, the top, but I chose the maximum instead. And the other caveat to this as well is the spatial resolution isn't as fine as like the data sets Jamshid was showing. So these are 25 micron spots because it's laser ablation, and they're 25 micron spacing as well. So it's a rather large crystal with not super great spatial resolution.
Okay, thank you very much.
Yeah.
And thank you for providing this tool for the community.
Yeah.
Other questions? And again, while we're waiting, so why did you take chromium? And you must have a whole bunch of other elements as well, right?
Yes. Yeah.
So is this because you have diffusion data only for chromium, or is there any other reason?
So this was the best one. So because we're doing laser ablation, iron and magnesium wasn't as confident in those timescales as with chromium. And then I looked at other rare earths, and those were giving some, I think one of the most crazy residence times was like 5 billion years. So I think we can safely say with good confidence that that one was not right. So Augustine is kind of a hot mess sometimes. So I don't think for this system that rare earths, at least with this data, it doesn't really work for Augustine, and it has really high water content. And there's a lot of things going on for this volcano. So rare earths might work in a different system, but with Augustine, it's not going to work because 5 billion is obviously wrong. And chromium was giving the most reasonable timescales.
Sorry, say that again.
The chromium with OPX was
Giving the most reasonable timescales. Yeah, I mean, I think, you know, one of the things, because people are doing so much of that, and, you know, you're modeling so many of these now, this is one way to look up where one may need to go back and look at the diffusion data itself. I mean, you know, so not the analytical techniques are getting better, but also the experimental techniques are getting, you know, many other options are becoming available. So it's just, I don't see, I mean, I was talking to Florian, who's, you know, a PhD student working at Hannover, and he was measuring things here, and he's looking at some things in feldspars, and he has used 3 different analytical techniques, none of which were available a few years ago, and you see differences in those things. So, you know, we are learning a lot about the experiments and the measurements themselves. So it's kind of it's very important to recognize it's a back and forth between, you know, modeling, seeing what works, and then improving the diffusion stuff as well. So
yeah, for sure. Yeah, and I think that's what I like about this code is you can quickly change what diffusivity you're using. So if, you know, a paper just came out with a new one, you could easily try it really quick. You don't have to redo all of the code. It's just a little simple change.
Right. Ralph, something?
Yeah, just related to the wealth elements, I think you see some zoning in the wealth elements, but it's growth zoning. You have different zones simply, and you can see that these timescales are absurd. So you already know from that this zoning was not formed by diffusion, also because you're not have a very high spatial resolution with your method that you use. And chromium is diffused faster, so you see it's always useful to compare more slowly diffusing elements and faster diffusing elements, and then by the comparison you can maybe elaborate. I mean, you should, in the ideal world, if all of these elements have diffused, you should get consistent timescales, but of course you need to also resolve the diffusion, the spatial diffusion scale, and so that's something you have to, of course, then think about and before just blindly using the timescales.
Yeah, that's actually what I was hoping. When I first started this, I was hoping that the OPX and the Plage would just nicely line up and be like, oh, look, it's pretty. And it worked, and that's not what happened. So I had to come up with a different way. And of course, like, I want to expand on this data set as well. Like, this is a pretty small data set for Augustine as well. I think it's like 11 Plage and 6 OPX, so it's still fairly small. So the future work I'm working on right now is adding, more like 100 plage and 100 OPX and hopefully 100 CPX as well. And then olivines if I can dig them out. And then just have like a whole huge mineral assemblage to see how they compare. And then one avenue we're thinking about with this code is, can it help find that? This is not a question for me, but more for the data science guy that we're working with, is there a sweet spot for a particular system of how many crystals you would need? Do you need, 1,000? Do you need 100? And where do the stats kind of start to even out on a particular system? Because that's a huge question right now, is how many crystals can you use to have a well-defined conclusion on that system?
So I hope the answer is not 1,000, but
Me too. Yeah. Yeah. As someone who makes their own crystal mounts, me too.
so let me see. I have something on the chat. I have to roll up the screen. Okay, so there's a question on the chat to everyone. In samples with serrate texture of minerals, which crystal generations, primary or youngest ones, are most important to study diffusion modeling to diffusion timescales processes, diffusion chronometry? So the question is, what textural type of mineral would you use to do diffusion chronometry with? Are there thoughts on that from people who are out here? I mean, I think, you need to look at the chemistry, but maybe, people who are more familiar with texture have ideas and thoughts on.
Well, I think sorry, Julie, Bryce.
No, you were the speaker, you should talk. I just was looking for my hand, but I think it depends on the question, right? And that's probably what Jamshid was going to say, is in the system. So, when Emma presented the Crater Lake question wasn't about eruption storage right before that eruption. We're trying to understand a much larger system. So understanding the rim on the basalts might not be as helpful to answer and give insight into a big system.
Mm-hmm. Mm-hmm. Yeah, I mean, I think that sums it up, that, you really have to define the question and then select the point of and, going back to, I guess, maybe Jamshid, that's what you were trying to say, that for you, you're looking at the inside part of the zoning profile. And so then the outer form is not probably that important, or?
Right, exactly. It depends on, I think, the processes that you're looking at, and also the time scale of them. That like with those crystals that I was looking at, if that deeper core rim boundary is on the time scale of weeks to months, then on the scale of an eruption that's occurring over weeks to months, it's I don't think that we have the resolution to determine what's happening in the days to hours in these little like micro zones within the rim. So I think that matters too. And as far as like texture or composition, of course, composition is important, is the most important, but I would look for things that are like euhedral nice boundaries, because if you look at like dissolution surfaces and you're trying to do diffusion across those, you can still get a time scale out of them, but then you're running the risk that first the crystal has to dissolve and then start growing the rim, and you've lost whatever amount of time. You don't know how long it took for it to dissolve to the maybe subhedral to anhedral core boundary between that and the rim. So that's something that we have to worry about, especially with reversely zoned like pyroxenes or olivines, for example. So I think that's something to keep in mind also.
Yeah, I mean, dissolution growth and diffusion is an issue by itself. I don't have your first name, but Asta, yeah, go ahead, ask question.
Hello, I have a question to Jamshid. Instead of using the magnetite ilmenite thermometers that you use in the trachyte pumice, instead of that, can we use any thermometers directly on basalt itself, like if we could?
Yeah, this is a good point. There are a range of different thermometers, geothermometers, and that exist out there. And we've tossed around ideas of doing various ones, but ultimately, I think the iron and titanium oxide is one of the most precise ones, and it's one of the highly dependable ones. So I think that because of the results in the trachyte are showing these temperatures that you would expect for a plagioclase amphibole bearing basalt, which is exactly the type of basalt that we have, I think that that's the most dependable one, because then we can use that temperature plus or minus 20 degrees, which is a narrower range than what you would expect for many of the other thermometers, that you might as well just approximate the temperature of the basalt. Whereas if you were to use like a 2-pyroxene thermometer, for example, is nice, but it has huge error bars, and also there's not really orthopyroxene in that sample. So we're pretty limited with what we can do. You could try to do some sort of crystal melt thermometry, but the error bars are so big, and it doesn't always work out. And it's already such a complex system, and the basalts are highly microlytic, so it's hard to get a glass composition affixed to some of the crystals. So it's definitely tough, and that's another assumption of ours. But I think I hope that I've convinced the majority of my audience, at least, that we can use the trachyte temperature for basalt. But at least we convinced the reviewers. So I guess that's the important part.
Thank you very much.
Answer your question. I mean, one of the issues is that, I mean, again, just like we were talking about the diffusion modeling before, you want to know what temperature you're trying to measure. I mean, the 2 feldspars probably give the temperature when the basalt may have crystallized, but if you're trying to model the timescale of interaction of the 2 melts, then the feldspar just doesn't readjust itself as quickly, and then maybe your ilmenite magnetite is more appropriate for that. So, and one of the important things to realize is that when you get different temperatures from different thermometers, doesn't mean that some of them are wrong. It could just that they be recording different stages of different processes. So.
Exactly. Thank you. Thank you. You worded it perfectly.
Yeah. Other questions? And again, related to the talk or general topics? So I had one for you, Jamshid, your time scale. So are those pretty typical of those kind of trachytes in elutions, or can you put that in a bigger context?
Sure. So we didn't do any diffusion modeling in any crystals from the trachyte itself. So we just used the temperature from the trachyte to do modeling in basalt. But as far as those timescales, like the order of magnitude of weeks to months, it depends on the volcano and the elutions. There's plenty of volcanoes that have not had diffusion chronometry done at them in the elutions, but in volcanoes like Augustine or Redoubt, another one, a project that I'm working on right now and hopefully submitting in the coming months, is at Redoubt, and the timescales there in clinopyroxene and orthopyroxene are years to decades, so significantly longer relative to Bogoslof. But then there are other volcanoes around the world that have shallow cryptodome forming eruptions, and such as Mount St. Helens or Ruapehu. And even though the volcanoes are very different than Bogoslof, you have pyroxenes there recording timescales of weeks to months. So I think in that type of, it's more about the process that's occurring rather than the mineral or the timescales. So it seems that our results are similar to other cryptodome forming eruptions that have weeks to months timescales. So in our paper, we kind of relate them to just the process occurring at Mount St. Helens and Ruapehu, but not saying that the volcanoes themselves are analogous, because they're obviously not. So hopefully that helps.
Makes sense. And then on the other extreme, Emma, the very long timescales that you were getting, what do you think of those? I mean, what might they be reflecting? Have you had time to think about those, or not yet?
I honestly have thought more about the Augustine than I have with the Crater Lake stuff because I've just started dipping my toes into that one. But yeah, especially with the really long time scales, at least with the Augustine one, that one I don't trust it as much. I'm not gonna lie. I wanna build up the data set there to see if it's a little bit more trustworthy, if there really is a difference. And potentially look at doing some EPMA work to get that spatial resolution down and see how it compares to the laser data that we have. And for Crater Lake, that one doesn't surprise me as much because it's a much bigger system where comparatively Augustine is tiny and doesn't have that central chamber. But yeah, with Crater Lake and Mount Mazama, like I think those are okay. I trust those a little bit more. That they're much, except for the ones that are super long. But yeah, still want to build up that data set too. I want more data before.
But you had what was it, 1,000,000 years or something in one of them? I mean that's pretty long for keeping something hot.
Yeah, exactly. Yeah.
So,
yeah. So for that one especially, because it's such a different system and I haven't really done a whole lot with calderas too, I want to narrow that temperature range a little bit more to see like what's more likely for those storage temperatures, and then look at the textures too, and different mineral assemblages to see what's really going on with Augustine. I'm a little bit more familiar with, and it's really wonky with the apatite in there too. So it's easier for me to throw out some of those profiles without worrying about it too much, because it's more apatite growing than diffusion.
So what was the temperature you used to get those 1,000,000 year timescales?
Those would be the colder ones. So I think that one was, let me look real quick, 8. Let me look here. I think it was 850.
I mean, I was just wondering when you're speaking whether there's room for the temperatures being different, something like what Jamshid was saying, that when you have the trachyte, but the temperature, or it was the other way around, for the basalt, you get the temperature from the trachyte. And whether, because I think, if you, instead of 850, if you change the temperature to something higher, the timescales would come down quite dramatically.
Oh yeah, for sure. I think the youngest one with that data set is 17,000, which is a little bit better.
It's not a bit better either, I mean, the timescales are right, and then one has to think about what the process is, or see whether the timescale may be different because of something that went into the modeling. I mean, that could be the diffusion data, that could be the temperature, that could be, I think those two, because things like boundary conditions and stuff wouldn't make that big a difference.
Yeah, true.
So, but yeah, I mean, it's just amazing that we can model that many diffusion profiles. The fact that, I'm just thinking about the fact that we even talked about the fact that we'll be modeling 1,000 crystals today. I mean, that was unthinkable. People are happy if they measure 2 profiles once upon a time. So, that's for major elements, not trace elements. Are there other questions from someone somewhere? You can type things into the chat or ask directly.
I have a question for the group, that something I've been talking about with some of my collaborators recently, and I thought I would pick the hive mind of the diffusion group. So something that I've noticed not only with my own results, but with other diffusion experiments, studies, sorry, is that if you're doing like diffusion chronometry for an eruption, usually your resulting timescales, the space between points becomes smaller as you approach the eruption onset or whenever the samples were erupted. And as they go further back in time, the space in between them becomes larger, like the space between timescales. So I'm wondering if there's, if you have any ideas for why. Is this a sampling bias, or are there actually less older timescales, or do you have ideas on the explanation for this? Because I have some of my own thoughts, but I've been debating it with my committee and collaborators. So I'm wondering if the diffusion hive mind expertise has some potential explanations for why we consistently see this trend.
So repeat that again. The trend is that closer to eruption, timescales are shorter, and when are the timescales longer again?
They're grouped together more closer to the eruption. If you want, I can show you. I can maybe show a figure of what I have in mind.
No, that would help.
Sure. Let me quick find this thing. Okay. Let me share my screen. Sorry. Thanks for humoring me. Okay, so here is a figure from readout Volcano, and you can see that so we're looking at products from the 2009 eruption, and the spacing between these timescales is quite close as it approaches the 2009 eruption, but then as it goes further away, the spacing between timescales seemingly increases. And the question here is that if this are these crystals just residual, that they're recording processes that happened in the 1989 eruption but weren't erupted, or is it some sort of a actual process that causes less timescales to be recorded older and further back in time? Because you can see this is on the scale of years to decades before the 2009 eruption. So this is kind of the question that I've been dealing with now, and I wonder if you have any thoughts regarding it.
Very good one. So yeah, I mean, please, everybody. Can be a number of different ways one could get to that, but let's hear what thoughts people have on that one. Anybody? No? Well, I could think of a couple of different things. The first thing is if the crystals sit in a magma chamber for longer, they tend to dissolve and grow. And so you could just be losing old crystals, even if they're chemically stable. So, or a magma mush zone or what have you. So that's one of the things that happen. The other thing is that if you look at other signals, if you look at seismic signals and things, those also have the same pattern, that you see a lot of tremors just before an eruption, and then they get more widely spaced out as you go back. So I don't know whether all of those imply new melt input, but that could be one interpretation, that you have more melt input happening just before the eruption, and that's probably why the eruptions happen in the first place. So, I mean, those are two thoughts. I'm sure there are other ways. Yeah, Leanne, please, go ahead.
Thank you. These are great talks, by the way. It occurs to me that some of the older ones, if they could be trapped more thoroughly into a mush zone that's more fully crystalline, and therefore simply be harder to remobilize during recharge events. And so you just have a smaller population. I'll also point out, and this is a small sample size, so I may be over interpreting the data, but if you look on your chart, starting with the eruption in 2009 and working back in time, you can see that spacing increase before the 1989 eruption onset, and then there's a little cluster right at 1989, and then the spacing increases even more. So,
agreed.
So it is a really intriguing question. Thank you.
Thank you. Yeah, this is what you said is exactly what I was trying to argue to my advisors, that I think that these crystals that are to the left of the 1989 were experiencing pre-eruptive processes leading up to the 1989 eruption, and then simply didn't get on the train basically for that eruption, and then are sticking around afterwards. So that's a really good point about being trapped in a mush for a longer time scale, harder to remobilize. And thank you, Shumit, for your feedback as well. I totally agree. I think that these are great potential explanations. So thanks for humoring me with it.
No, this is, I think, this is, again, I mean, what I can say is that there's a kind of density of data we haven't seen. We're only beginning to see these kinds of, these amounts of data so that we can even begin to start thinking about these questions. I mean, we're used to be that we got 3 or 4 timescales and that was it. And we did what we could with those. So this is also from your thesis, Jamshid, or what is this?
Yes, so this is from my third PhD project where we're doing diffusion chronometry and interdisciplinary synthesis at readout. So this is a much different system. The black dots here are representing from low silica andesite, and the white is from intermediate to high silica andesite. So you can see that there's a specific trend with the low silica andesite not showing up until this interruptive period as well. So we have lots of fun interpretations and interdisciplinary synthesis that's happening on this one, but this was a diffusion specific question that I had for the community. But I'm hoping to submit this this readout diffusion and synthesis paper in the early fall. So stay tuned, please.
Thank you. This looks like a great data set.
Thank you.
Other questions for Emma or for Jamshid? Quickly. Well, I don't see anything. Yeah, very interesting question and ideas about data.
I have a question if nobody else does, kind of like James.
Go ahead.
Okay. Like you said, hive mind. I was wondering if anybody knows of experiments held at temperatures and allowed to diffuse in the melts. It would be great to have those, build those in to like validate the MSURFED model. So I was wondering if anybody knew about those kind of data sets.
So data for what again?
Just experiments that are held at certain temperatures and allowed the elements to diffuse in the melts.
Oh, into the melt. Well, you have to look, there are a few around. I mean, I remember one study by Jurovich and Watson back in the 80s, and Spandler and O'Neill are a few. I'm sure there are others. You'd have to search them, but there are numbers around.
Yeah, I think so this is this discussion Em and I are having. We're trying, because the experiment with the published data, those data from some of the older experiments are hard to find in the spatial resolution. But if you can imagine having, instead of the volcanoes running the experiment regularly, but there are all these other parameters we don't know about, but if there are sort of experimental charges that are around that have been held in a temperature and a disequilibrium system that are then evaluated for diffusion, they would be a beautiful data set for validating MSURFED.
We have some, and we have some very curious results, which you should be writing up soon, I hope.
Oh, cool. Okay.
And the reason it's not published is because I've had a couple of different master students look at things, and so if you have so what we did actually was, so we did that Carl et al. Study on Mount Etna, where we looked at olivine things. And then it occurred to us that we could do that experiment in the lab, just what you're saying. So we could take the olivine and put it in a melt, but you can make the melt be in disequilibrium in 2 different ways. You can make it be in disequilibrium such that new olivine grows on the old olivine, or you can have it such that the old olivine just dissolves away. And turns out you have difference in behavior if you do that. And we're trying to sort that out and work it out. And so, yeah, I mean, that's where one place I know the data exists. I mean, exists in our drawers at this moment, but should be out hopefully sooner.
Right.
But that's an experiment that is quite straightforward to do, actually.
Yeah, that would be really cool, because that I think would help, and that would help also with some of the fitting parameters that came up earlier and optimizing.
Yeah, but sorry, go ahead.
No, we're just trying to be honest brokers of the conditions, right? Because we can't control some of these temperatures in some of these systems. So that's where we're showing the possibilities, but we're mindful that some of the timescales are on the long side. So being able, possible timescales, so being able to trim that down would be really helpful. So
Yeah, so that's from what we have. And again, we're trying to still figure out what it all means. But from what we have now, it seems like it's throwing more twists into the business than we've been aware of until now.
Mhm.
So
Cool.
we'll see how it comes
Yeah.
out.
Yeah, well, keep us posted. That's great. Thanks.
Yeah, so thank you, Emma, for asking. That allowed me to do a advertisement for work in progress. And I actually know Tom Shea has been doing some similar experiments as well. So yeah, that's happening. I mean, those are experiments that are definitely doable. Anything else from anyone else? If not, it's time to say thank you again to Jamshid and Emma in particular, but for everybody else for being here and asking the questions and participating in the discussion. And we will have one more of these in June, and then we go on a summer break. So we have John Blundy, and we're trying to find a second speaker for the next session. So we'll see, we'll send out the advertisement when we have the speakers. In the meantime, keep discussing and yeah, the other thing I wanted to point out to you, Emma, is that we on the website where we have the talks, we also have a place where you can put software. So once you're ready to put your software out, we'd be happy to put it on the web page with a link to your GitHub site or whatever you have it there.
Yeah, awesome. Thank you.
That'd be good.
Yeah.
Okay. So thank you, everybody, and goodbye till the next time.